Okay, in this video we're going to talk about the power set. The power set in set theory is the set of all subsets of whatever parameter it takes. So in this case, P of A is the power set of A, which is a set of all subsets of A. So let's see an example of this. So for example, if A equals little b, and little c, these are the elements of the set A, then the power set of A is going to be all possible subsets of the set A. So if you recall, the empty set is going to be in there. Recall, the empty set is a subset of every other set. We did a proof on that in a previous video. All right. So if we're doing the power set, which is all possible subsets, well, the empty set has to be in there. And then we have the set containing A, the set containing B, set containing C. So you see, notice the power set is a set of sets. So each element in the power set is actually going to be a set in and of itself. And then we have AB, BC, AC, and finally every set is a subset of itself. So we have A, B, C. There we go. So this is the power set of A. Now, something to notice is here the size of A, this is one way of writing the size of A, is going to be 3. There's 3 elements in A. So what is the size of the power set of A? Well, we've got 1, 2, 3, 4, 5, 6, 7, 8. And we're going to do a proof about the size of the power set here in just a moment. So what I'd like to prove is that if a set has n elements, that its power set has 2 to the n elements. Let's see if that works on the previous slide. So here, n is 3. So if A has n equals 3 elements, so the power set of A should have 2 to the n, which is 8 elements. So in our little example, this seems to work. Let's do a proof to prove that it will always work. So I want you to stop and think about it. What kind of a proof are we going to do for this? If we did a direct proof, then I don't know how you would go about that. What we really have is a sequence, right? N could equal 0, n could equal 1, n could equal 2, n could equal 3. The size of A could go anywhere from being empty to having, an arbitrarily large number of elements. So this just calls for doing a proof by induction. So we're going to start with the base case. So what is the smallest value n can have, n can be? Well, it could be 0, right? A could equal the empty set. You can't have negative number of elements, but you can go down to 0. So as we said, the only set with 0 elements is the empty set. So how many subsets, what would the power set of the empty set be? So the power set of the empty set is just going to be the empty set, right? Because the empty set is always a subset of every set, including itself, the empty set. Okay, so the only subset of the empty set is itself. Therefore, the size of the power set of the empty set is going to equal 1. Okay, so let's take a look. So let's take a look at this formula, 2 to the n. Also, 2 to the 0 is equal to 1. So since both are the same, the base case holds. Okay, let's go on to our inductive step. Okay, so our inductive step, first we need to have the inductive hypothesis. Pause a moment and see if you can figure out what the inductive hypothesis would be. In fact, take a moment and try to do the rest of this proof. Okay, so the inductive step, we're going to suppose that this all works when n equals k. Okay, what do we want to show? We want to show that the whole thing works with k plus 1 elements. Okay, so recall, whenever we want to do this proof by induction, we're going to start from sort of one side, one direction. So I'm going to start with a set that has k plus 1 elements and see if we can figure out how to use the inductive hypothesis. So let A be any set with k plus 1 elements. Now notice k is at least 0, so k plus 1 has at least 1 element. So we know we have at least one element, so I'm going to pick any element. in A, and I'm going to call it X. Right. So what I'm doing is I'm using the element argument in this proof by induction. So what we have is we said we've got this set A, and it's non-empty, and it's got at least one element in it. So I'm going to go through and I'm going to pick at random one element in A, and I'm going to call it X. Okay, so I'm going to draw my little picture over here. We have the set A, and we have an element X. Now notice that any subset of A either contains X or it doesn't. Right? We could have a subset here of A that contains X, and we could have a different subset here that doesn't contain X. Okay. And that's true even if A only has a single element, X, because the power set would then have X and the empty set. So the empty set would be a subset that does not contain X, and the set with X would be a subset that does contain X. So this is always going to be true. Well, any subset that does not contain X is also a subset of the set of A prime, or A hat, which is equal to A minus the set minus X. Right? So A hat looks very similar to A. It's just instead of X, there's now a little hole where that X used to be. It has everything else from A, but it does not have X anymore. This is A hat. Okay, so what is the size of A hat? The size of A hat equals A minus X is K. Because remember, the size of A is K plus 1, and we just removed an element, so A hat has one less, which is K. And by our inductive hypothesis, I know what to do about a set that has K elements. I know that A hat, which is equal to A minus the set containing X, has a power set with 2 to the K elements. Now, I'd like you to notice that any subset of A hat can be matched or unioned with X. So, for example, so this isn't part of the proof because examples don't belong in proofs, but this is going to help illustrate what I mean by this sentence. If the set containing A and B is a subset of A hat, then subset containing A, B, and X is a subset of A. Right? Because I can match that X with all the subsets in A hat. This means that there are the same as many subsets of A with X as there were subsets of A hat without X. Right? So A hat has 2 to the K subsets, and there's going to be at least 2 to the K subsets including X, because we can add X to each one of those subsets of A hat. So since there are 2 to the K subsets in A hat, which recall was A minus X, there are 2 times 2 to the K, which is 2 to the K plus 1 subsets in A, right? The 2 to the K that include X and the 2 to the K that don't include X. So therefore, a set with K plus 1 elements has 2 to the K plus 1 subsets, which is what we were trying to show. Right? We want to show that a set with K plus 1 elements has a power set with 2 to the K plus 1 elements in it. Well, the power set is just a number of subsets. So the power set of such a set has 2 to the K plus 1 elements, which was to be shown. So there we go. So now you know a little bit about the power set, and we've done an interesting proof using the proof by induction using the element method to prove the size of this power set.